Hello everyone, welcome to this session on graph neural networks. My name is Mario Santa Cruz. I am part of the team developing AIFS and the Anemoy ecosystem, and I will be guiding today through this presentation on graph neural networks. First of all, let's start with a brief introduction of the session. We will start motivating the graph neural networks, why are they useful. Following, we will be presenting its core principles for design and also the different types of graph neural networks that we can see. Later we will present the message passing algorithm, and then we will go for some use cases, examples in the weather forecasting area that you can take as an example for other use cases like downscaling, time interpolation or others. So first, start coming back to the previous lectures. We have already introduced the neuron that we stacked to get like a layer, and then we took those layers and stacked to gain this to have like a more deeper neural network, or like an MLP. And we also presented the convolutional neural network, that it was like this 3x3 filter or 5x5 filter that was applied across the whole 2D field. So in this case we presented two different neural network blocks or layers, one applied to one dimension and the other one applied to a 2D grid. But this convolution, it was really nice because we could extract some local patterns, but it has some problems, or it makes some assumptions that in this case those assumptions refer to the data. So we assume that the data is defined in a regular or rectilinear grid. We also assume that there is like a fish local neighbor, right? Because as it is like a regular grid, we know that it is always surrounded by the same number of grid points, pixels for an image. And then we also assume that it is like translation and invariance, right? We apply the same kernel across the whole 2D field. And some of these things, it may be useful for a lot of use cases, but there are use cases where they don't apply. One of these can be earth science models, where we have like a sphere grid that can have multiple levels, like model levels, pressure levels, and also we have, in this case of the sphere, the important part is that we will have singularities in the North Pole and the South Pole, and also like in the lateral boundaries. So it is, if we consider that as an image, it may be that our models, our neural networks, may produce some artifacts there because the lateral boundaries, they are not connected, or the poles, they may get like some strange values there, right? So in that sense, that can be a problem. And the other thing is that a lot of the most modern numerical weather prediction systems, they produce the output in an unstructured message. So that's the example for Icon and AI Icon, that they produce their own mesh, and also for IFS and AIFS, that they produce the result in a rectilinear reduced Gaussian grid. So in both of these cases, what we need is another data structure that doesn't have these limitations. And here is where we introduce the graph. The graph is just a tuple of nodes and edges. The nodes in a Earth system component problem can represent location, and the edges will represent relationship. In the case of Earth science, this relationship can be distances, can be any other thing, but these graph neural networks are also these graphs are used across a lot of different use cases and fields. So this is the example, for example, of social networks, where we can represent with nodes different people, and then with edges the connection or relationship with them. It is also used for representing molecules, where we can use this same graph structure, and again for transportation. So probably all of your navigation apps, they will use graphs for representing the problem, where the nodes are different locations in the maps, and the edges represent the ways to go from one node to another. And these edges will have features like the distance, or like the type of road that you go from from A to B. So all of these features relates to the edges that connect two nodes. And then we have also this concept of the knowledge graphs, that this is just try to encapsulate knowledge from a text or a database. And the idea here is that you have entities that relates with each other, and these relationships are represented by the edges. So the graph is quite a general data structure that it is useful for a lot of problems. So here, what we have to understand is that the graph neural networks are just a type of neural network that are applied to graph. It is not a new layer like the linear layer and then the convolutional layer, but it is like a neural network that it is applied to a different data structure, right? That it is the graph. So in this sense, this means that we have a graph as an input, a graph as an output. It doesn't have to be exactly the same graph, but the idea is that this model, this graph neural network, will take some graph as an input, will do some operations, and the output will be again another graph. And similar to the linear layer, where we could use that last linear layer to produce different results, to forecast like a probabilities of different classes, or to forecast like a regression problem, like for example, a post-processing algorithm for correcting some biases in some observation, something like that, right? Where you predict a value, not a label. So this is still the same with graph neural networks. You can do different tasks. One example of that is like the node classification, where you assign one label per node. This is still possible. Then you have like another use case like link prediction, where you, instead of the output of the model, instead of being around the nodes, it is more focused on the edges. So this link prediction is used for system recommendations, where they try to predict what are the new connections. Imagine in this case that the nodes are different films or different books, and the connections is where ones are related to each other or are interested for a given user. So in that sense, creating new connections, it is always useful for this recommendation system. Then we have also graph classification. So instead of predicting one label per node, we can predict one label for the whole graph. This is called graph classification, and it is used in things like protein classification. And then the last thing that is probably the most interesting for us working in earth science is like the node regression, where for each node in our final graph we forecast one value or multiple values. If they refer to multiple variables or to multiple pressure levels, it doesn't have to be a single scalar, but it can be like a vector of values. So here, just coming back, we have motivated why it's important to have the graph, this data structure to represent unstructured information. And here it's just important to remember that the graph was two things, right? The nodes and the edges, both of them having features. And what we want in this graph neural network is that in each of these layers, we are updating all of the time these node and edge features, right? Similar as we were doing in the linear layers, that we have like one vector, and at each layer we were producing like a new vector or latent representation. And for the convolution it was the same, right? We have like a spatial field, and in each layer we were producing a new spatial field, a new spatial representation. So the idea with the graph would be the same, producing a layer that just updates the node and edge feature at each step. And in this regard, we have to think what inductive biases should a graph neural network have. And here there are two that we are interested. First of all is the locality. Similar to the convolution, we want to update the nodes only based on those that are connected, right? You similar to in the convolution, you were always applying this filter across the whole field. And here in the graph, we will also want to update some values based on the nodes that are connected to it. And the other property is the permutation invariance. in temporal sequence, it's important that the nodes are ordered. For example, imagine weather forecasting where you are passing multiple time steps. You want that to be always ordered because the temporal relationship is important. In that case, here the spatial relationship is inferred by the edges, so you want to use the edges to express the different distances within the nodes, and in this case you want to be permutation invariant, so the order of aggregating the nodes is not important. And in this regard, with these two things, the most common algorithm for graph neural networks is what is called message passaging, that it has like 3 or 4 stages as you consider. The first part to understand is that let's put the example, right? I will be like the yellow node there in the diagram, and I want to update my representation, my futures, right? So for that, any of the nodes that are connected to me, all of the users that are looking at this lecture, you will have also a node representation, right? So the first part is create your own messages. For creating these messages, you will use your own node representation and also the edge coming from you to me, that for each of you will be different. So after that, a lot of you will create like a lot of messages, right? And you will send those messages to me, like the target node. I, as the target node, will aggregate all of those messages together with an aggregation function. This function is the one that has to be permutation invariance. So for example, an addition is something that it is permutation invariance because it doesn't matter the order of the sequence. And then once that I have aggregated all of the messages that are coming from all of you, I can update my node futures based on the final message and my own node representation. That's the final step represented here in the update state. Here, the idea is that the aggregation function, if it's used like a weighted mean, a weighted sum, in this case, it can be seen as a convolution, right? So it is just this convolution still appears with this graph structure. It is not like a new layer, new type of neural network layer. And similar, as you remember from previous lectures, we needed 3 things to scale our performance to the state of the art. One thing was having more data, other thing was having more compute, and the third one was scaling your model, right? And for scaling your model, you could go deeper, introducing more layers, and this is still the case with the GNNs, right? When you want to scale your GNNs, you will stack multiple GNNs on top of each other. That all of them, for sure, have to be this permutation invariance aggregation function. So just to finish more on the graph neural network details, there are 2 things that we haven't mentioned and they are very important for graph neural networks in practice. First of all is that these MLPs, this linear, when I've said like a couple of times, update your node futures, creating the messages, all of this means to use most of the time linear layers, right? So you have your own representation and your edge futures, and you use like an MLP to create the message, right? So these MLPs are shared across all of the students, all of the people attending this course. You don't have your own MLP for your case. So in this case, it's quite important. You will have less parameters, but it is also more similar to the convolution, right? Remember that for the convolution, you had one filter with just a few parameters that you were rolling out over the whole spatial field. In this case, it's exactly the same. We use the same MLPs for creating the messages, for updating the edge futures, for updating the source nodes, and for updating the target nodes. For each of those, independently of which node are you in the graph. So you will use one linear layer for the source node, you will use one linear layer for the target nodes, you will use another linear layer for the edge futures. And the nice thing about this is, as all of these operations are differentiable, you can still apply the principles that we explained in previous lectures of backward propagation, right? As all of the operations are propagations, you can compute the loss score, and then with that loss score, compute the gradients and update the model parameters. And the other important part is that this graph will tend to be very sparse. And one nice property that they have is that you can split them, you can split the graph by the target node, for example, and this is what it is intended to be represented here. So you see in each color is differentiated by the target node that it is connected, and the idea is that you can split by target node, and this is a very nice property because it makes things very easy just to parallelize, which is important when scaling your models to millions or billions of parameters, and they don't fit anymore in one GPU, and you will need to shard that graph into multiple GPUs. This is quite nice because it will allow you to split the graph in different GPUs. So now let's go to the overall design of these graph neural networks, more target for the case of earth science. Do you remember this structure that we presented in some of the previous lecture? Yes, if you were thinking about the unit or the encoder, processor, decoder, you were right. We have already talked about this design in where we have this U-shape where we try to encode, then we have like a processing step and then a decode. Here it's important to see again that we have our initial resolution represented at the beginning and at the end, and then in the middle, in the bottleneck, what we have is a way coarser representation, right? So we see how we shrink the spatial field of our latent representation as we go through the encoder, and in the bottleneck we have the coarsest representation that we'll have through the whole network. So this is still applies to the graph. And the case is that in the graph, for example, in a global problem, we will have like a mesh represented by our data. So imagine era 5. And then for this mesh, on top of this mesh, we create like another mesh or set of nodes that we normally call hidden nodes, latent nodes. You can hear both options. And in this case, we use this as this coarser resolution of the processing, right? So we split our model in these three phases, this encoding, processing, and decoding. The encoding is represented by as a graph going from the data nodes to the hidden nodes. Then the processing is represented by another graph going from the hidden nodes to the same hidden nodes. And then we have the decoding that are edges going from the hidden representation back to the data, so to the mesh of the physical variables. In this regard, one example that we have from the literature is GraphCast, one of the first models that we have with this structure, where they were using this encoder and decoder. As you can see in the images, they are very local, they just have connections from the closest grid points. And then we have the processor. The processor, yes, in this case is a multi-mesh message passing. What does it mean? This means that it has edges of different scales, so it has edges going edges of length of a few kilometers, and then edges of a few hundreds of kilometers. The motivation with this is that the model is able to propagate small scales but also large scales from one part of the globe to another. So it is still interesting to know until what scale you should include, but it will depend on your use case, on your temporal resolution, and also on your spatial resolution. And then another case is the AIFS, our data-driven model at the GNNs, and in this case we have a similar structure: encoder, processor, decoder. The encoder and the decoder are very similar. They are graphs going to a hidden resolution, but there is here like a significant difference that it is in the processor. And in the processor, what we do is just consider the mesh of the processor as a sequence of points, and we treat that as a sequence as a time series problem, where we just use transformer that will be introduced later in the course. But the idea is that you have like a convolution but over one dimension, and this kind of window is rolled over the whole globe, just updating the hidden representation, right? So that's the main difference between GraphCast and AIFS, is this processor that in GraphCast is another graph, but in AIFS is handled as a sequence modeling problem. But here the nice thing about these both approaches are the encoder and processor that handling consider them as graphs. It allows us to have a lot of flexibility with our data. So this is the case, for example, with GraphDoc, that is this model that works with for direct observation prediction, and we take observation both in the input and in the output. So we would expect that it works good for gridded observations, for stations, but this also works really nice with dynamic observations, as we can only have to connect those with the nearest neighbor, but this graph structure is quite flexible to that, to don't have like a rectilinear grid, as you can see in the right, where we have stations. Using a graph structure is very easy to understand and also to process this information to the observation locations. So with this we have covered most of the important cases in forecasting that you can extrapolate to your use case. So this can be also useful for time interpolation, for downscaling, for emulation, for any other of your tasks. You probably can frame it as a graph neural network. And in this case, it's important to mention some of the most useful tools here. One is PyTorch Geometric. This is used across all of the domains and is built on top of the Torch ecosystem. And then we have Anemoy Graphs, that it is a tool built inside of the Anemoy ecosystem that is used to build and customize and inspect your graphs in earth science problems. So around the to build graphs in the earth with different methods used for building models like GraphCast, but also like AIFS or AICON or Breeze. So it provides a lot of functionality and also plays really good with PyTorch Geometric. So these are some of the most interesting tools for you that we will learn through the hands-on session. But it's important that you can check those references later if you want to know more about how to use it. And then later, the last slide, I would like to include some of the most important reference about graph neural networks in weather. So you could go there and check from the authors their implementations, their design choices, and their motivation for all of their solutions. So thank you very much for attending the lecture.